which is now. William, the floor is yours. So, by the way, you're still muted in case you were already saying something.
Okay, there we go. Sorry, I got
There we go. No worry.
muted, and then I had to open the slides. The shortcut keys weren't working.
Sure.
Okay. So today I want to tell you all about a notion of minors for lattices enriched with a generating set. And then from this, I'm going to look at a poset that we make out of these minors. And we'll see that these are rather well-structured posets. I want to start with looking at an example so I motivate where we're going though. So here on the left, I just have a poset, and at the top, you see there's a graph there, this 3-cycle graph. The elements in this poset are all the minors of this graph, which are simple. And we're considering here the edges to be unlabeled with the vertices labeled. So for instance, at the top, you see the 3 results of deleting an edge. And then 2 levels down on the far left, this is a simplification after we contract by the edge between 1 and 3. And when we do that simplification, it doesn't matter which edge we pick because the edges are unlabeled. And then on the right here is my depiction of a regular cell complex. And it turns out that this poset here is isomorphic to the face poset of this cell complex. These posets of simple vertex labeled minors for graphs show up quite naturally as lower intervals in the well-studied uncrossing poset, a certain poset on complete matchings. And this poset is known to be isomorphic to the face poset of a regular cell complex. And so for these graphs that show up as these lower intervals, we always have that they're telling you a regular cell complex, which is a sphere. The only graphs that works for, though, is ones with embedding into the 2 disk with all the vertices lying on the boundary. And that's just because of how you associate the graphs with bearings. In this talk, I'm going to extend this result not only to all graphs, but beyond this to any polymatroid. So that's where we're headed. And I want to give you an outline of the talk. We're going to start by talking about generator-enriched lattices and minors of these. And then I'll go on and talk about how these lattice minors relate to polymatroid minors. And we'll introduce a minor poset for any generator-enriched lattice. And I'll give a zip construction for these minor posets, which will give us some corollaries showing that these are very well structured. And if I have time, I'll talk about some cd-index inequalities that we get from this zip construction. Okay, so definitions this should set up. Lattice is poset, and any 2 elements have a least upper bound, which we call a join, and a greatest lower bound, which we call a meet. And I have the conditions for those written out. On the right, I have a Haas diagram of 2 different lattices. So the top right is the rank 3 Boolean algebra. Here the join corresponds to unions, and the meets correspond to intersections. Below that is another lattice, just for 5 elements, and this will be a running example for the talk. An important notion would be join irreducibles. So this is an element of the lattice which covers exactly one other element. In the Boolean algebra, the join irreducibles are 1, 2, and 3. And in the lattice below, the join irreducibles are A, B, and C. And this corresponds to like the usual notion of algebraic reducibility with respect to this join operation. Okay, and I'm going to denote that at the bottom as it says E or L. Now, a generator-enriched lattice is a pair consisting of a lattice L and a generating set G, which does not contain the minimum element. And furthermore, it generates the lattice via the join operation. Some notation for this. if I sort of already know an ambient join operation, so I have a lattice and I'm going to specify another generator arranged lattice inside of that. I can do this just by telling you the generating set and the minimal element. And so I'm going to note that with these angle brackets, X for the generating set bar, Z for the minimum element. You can depict generator enriched lattices with a diagram, which is analogous to Cayley graphs for groups. So the vertex set is the directed graph with vertex set the elements, and each edge corresponds to going up by a generator. On the right there, these are the diagrams for the two lattices on the last page when they're enriched with the set of joint irreducibles. So in the first one, we get a couple extra edges from the Haas diagram, which correspond to going up by a joint irreducible. And you can read off the generating set. Here it's A, B, and C because those are the things incident to the minimum. And then you'll notice also the Boolean algebra just happens to be the same as the Haas diagram. Just as a fun fact, that happens exactly when the lattice is geometric and the generating set is the atoms. All right, so now I can tell you about what minors of generator enriched lattices are. So if I have a subset I of the generators, the deletion by I is formed by just removing those generators, and then the new lattice is whatever we, whatever is generated by the remaining generators. And we have the same minimum element in that. On the other hand, the contraction, so I have a formula there written out. That's a little tough to read. But the idea is that you're just joining up with everything in your set I. So our generators are one of the old generators join everything in I, with the caveat that if that might equal just the join of everything in I, which is the new minimum element, so we have to take that out of the generating set. And then when I say a minor of a generator enriched lattice, I just mean anything you can get by deletions and contractions. Here's some examples. On the top left, this is the face lattice of the square. I've labeled the elements with what their vertices are, and the generating set is the four atoms, 1, 2, 3, and 4. On the right, that's the result of when you delete the generator 1. So we lose 1, and we also lose 1, 2, and 1, 3. None of these can be expressed as a join of just 2, 3, and 4. But on the other hand, we still have the element 1, 2, 3, 4 because that's a join of 2 and 3. In the bottom left is the result of contracting original lattice by the generator 1. So we get 1, 2, and 1, 3 as generators coming from 2 and 3. We also get 1, 2, 3, 4 as a generator because that's a join with 1 and 4. And then bottom right is if I take that contraction and delete the generator 1, 2, 3, 4, I still have the same lattice. 1, 2, 3, 4 is no longer a generator, but it's still an element since it's a join of 1, 2, and 1, 3. Okay, so that's our notions of minors for generator enriched lattices. Now I want to talk about how these relate to graph minors and more generally polymatroid minors. Okay, so the statement here is that all the simple vertex labeled minors of a given graph, as I defined on the first slide at the beginning of the talk, are in bijection with the minors of the lattice of flats. And this bijection is we just take a graph minor and send it to its lattice of flats. There's a bit of caveat here in that I have to, in how we label the lattice of flats, especially since the edges are unlabeled. So as an example here, I have this graph G in the top right, and to its right is its lattice of flats. Here the flats are labeled as partitions of the vertices, and these are just all the partitions you get as whose blocks are the connected components of a subgraph. On the bottom left is the simplification of the contraction of this graph by 1, 2, and its lattice of flats. And you can see you can get that from the original lattice of flats by contracting by the corresponding partition, which has 1 and 2 in the same block. And then the bottom right is the deletion by the edge 3, 4, the fifth lattice of flats. And in the original lattice, that corresponds to removing the partition with 3 and 4 in the same block. Or, more accurately, deleting it, because we also lose the stuff, elements above it. In general, the idea of the bijection here is that given a graph minor, the vertices are labeled by blocks of a partition of the original vertex labels. Those blocks tell you the blocks of the minimal partition in the lattice minor, and then each edge connects 2 blocks, and that corresponds to a generator, which you get from the minimal partition by merging the corresponding 2 blocks. Now, as it turns out, this bijection actually generalizes beyond graphs and holds in a certain sense for any polymatroid. So I'll get to that, but first I want to introduce polymatroids real quick to make sure everyone's on the same page, and we'll have to see how they relate to generator enriched lattices. Polymatroid is a set, or is a function on a ground set on, excuse me, getting mixed up. Okay, but this is a function from a Boolean algebra of all subsets of a given ground set to the non-negative real numbers. And we have to satisfy these 3 conditions here. So we have to take the empty set to 0. This has to be an order preserving function, and it also has to satisfy this submodularity inequality here. If you were to also say that the function values were integer values, and that so R of x is bounded above by the size of x for any set x, then this would be the rank function definition of a matroid. Some terminology for polymatroids: 2 elements of the ground set are parallel when the singletons have the same rank as their union, and then a loop is an element with rank 0. We're going to be interested in this closure operator associated to a polymatroid. This is a map on the Boolean algebra, and the closure of a set is computed by adding in all the elements which don't increase the rank. And you can show easily from the submodularity that necessarily the rank of a closure of a set and the rank of the original set is the same. So now we can associate to any polymatroid a generator enriched lattice. These closed sets are commonly called flats, and they're well known to form a lattice when ordered under inclusion.
Can I ask a short question?
Oh, of course, yeah.
Sorry about those polymatroids. Are there any like natural mathematical objects that are polymatroids but not matroids?
I'm not real read up on this, but I think there are good constructions that Jack Edmonds has given when he introduced them.
Okay. Cool. Thanks.
All right. So where was I? So we have a lattice of flats for any polymatroid, the closed sets ordered under inclusion, and we can form a generator enriched lattice of flats where the generating set is a closure of all the singletons which aren't loops. So I have 2 examples of that at the bottom here. On the far left is it's a polymatroid. I've got the rank values written on the unlabeled Haas diagram of the Boolean algebra. And just to its right is this lattice of flats. So for instance, 1 and 2 is a generator because that's the closure of the singleton 2. And the other generators are just the closure 1 and closure 3, which are themselves. On the right is another example. And here we have 1, 2, 3 as the generator because that's the closure of the atom on the right, singleton 3. Now, as it turns out, this generator enriched lattice of flats is encoding the simple information of the polymatroid closure operator. In fact, generator enriched lattices of flats correspond or relate to polymatroid closure operators in the same sort of way that geometric lattices relate to matroids. And before I can give a precise statement of that, I need two definitions. So, a strong map between two generator enriched lattices is a join preserving map on the underlying lattices. And it also satisfies this condition that any generator in the domain is sent either to a generator or to the minimum element. I call this a strong map because it's a straightforward generalization of strong maps of matroids, or simple matroids at least. One definition of a strong map between simple matroids is a join preserving map between the lattice of flats where atoms go to atoms or the minimum. And a strong surjection has to satisfy that all the generators in the codomain are mapped to by a generator. This necessarily implies that the map on the underlying lattices is surjective. I also need this notion of a closure operator. This is a standard construction from theory of Gavlov constructions. But given any strong map, the associated closure operator is computed by taking an element to the join of every other element in the lattice L, which has the same image as it. In other words, this will take it to the largest element of that image. Okay, with that, I can give the statement of how generator enriched lattices relate to polymatroid closure operators. If we have ground set E, then a closure operator in the Boolean algebra is going to be the closure operator of a polymatroid whose generator enriched lattice of flats is isomorphic to some given generator enriched lattice LG, precisely when it's the closure operator of a strong surjection from the Boolean algebra onto that generator enriched lattice. I said this was analogous to the connection between matroids and geometric lattices. A matroid can be equivalently defined as a strong surjection from a Boolean algebra onto a geometric lattice. Here's a picture at the bottom here with a example. We already saw this polymatroid, and in the middle, this is its generator enriched lattice of flats with different labeling. On the right, that is both the closure operator of the polymatroid as well as the closure operator of the map from the Boolean algebra. It sends 1 to A, 2 to B, and 3 to C. You can see on the polymatroid, the 3 bolded edges correspond to where the rank values don't change. All right, so that's all I want to say about polymatroids. And next I want to go into this poset of minors for generator enriched lattices. Oh, sorry, I forgot. There's one more thing about polymatroids. I never got to generalizing the connection between lattice minors and graph minors. So that's where we're at now. So we need this notion of a parallel closed pair. If I have a polymatroid, parallel closed pair is a pair consisting of a flat F and another polymatroid S, which is a minor. And specifically, it's a deletion of the contraction by that flat. And then the third condition is that the ground set of S has to be a union of parallel classes from that contraction. Now with that, our theorem here is that for any polymatroid, the minors of the generator enriched lattice of flats are in bijection with the parallel closed pairs of the polymatroid. At the bottom here, I have a couple diagrams which are showing how these parallel closed pairs relate to the simple vertex labeled minors for a graph. On the left is some graph. Just to the right of that is a contraction by a flat. You can read the flat off from the labels on the vertices. The corresponding partition has blocks 1, 3, 8, 2, 4, 5, and 6, 7. Just to the right of that is a parallel closed pair viewed as a graph. Since I deleted that one edge on the left of the sort of triangle shape, I delete the other one as well. And to the right of that is the simplification of it, which is the corresponding simple vertex labeled minor. I can go back from the simple vertex labeled minor just by adding in any edge parallel to one in that minor. Okay, so these parallel closed pairs are one way to generalize this to the setting of polymetroids. Okay, so now I want to go on and talk about this partial ordering of the minors of generator enriched lattice. So here's our definition. Given a generator enriched lattice, LG, a minor poset, I'm going to write MLG. It has a unique minimum element, empty set, and as well as all the minors of the generator enriched lattice. And the ordering is minor of, or in other words, we go down in this poset by doing deletions and contractions. Here's an example. The top, that's the 5-element lattice. That's a running example in this talk. And some interesting things to point out. At the bottom, you can see the rank 1 elements are corresponding to the 5 elements in the lattice. Just above that, there's 7 elements at the second level, which correspond to the 7 edges in this diagram. And you can also see that this poset is ranked, and the rank function is given by the number of generators of a minor plus 1. So at the bottom, we've got minors with no generators, and then 1 generator, 2 generator, and then there's just the top element with 3 generators. Some basic facts about minor posets in general. These 3 things I pointed out in the last slide always happen for any generator enriched lattice. The minor poset is graded, and the rank is size of, or the number of generators plus 1. Rank 1 elements correspond to all the elements of the lattice, and rank 2 elements correspond to all the edges of the diagram. Furthermore, this poset is thin, and that every rank 2 element forms a diamond. They'll be useful later. There's 2 classes of lattices for which we can easily compute the minor poset. I have a nice form. First being minimally generated Boolean algebras. So it's not too hard to show that any minor of a Boolean algebra has to be an interval that just kind of comes out because the joins in the Boolean algebra are free. And the interval, so the minor poset here is isomorphic to the interval poset, and that's isomorphic to the face lattice of a cube of 1 more rank than the Boolean algebra. On the other hand, if we look at a chain, the minor poset is isomorphic to Boolean algebra of rank 1 more than the chain. This follows because in a chain, every element except for the minimum is a join irreducible, and thus I can get any subset of the chain as a minor. If I want to remove something which is not the minimum, I can delete it because it's a generator. And to remove the minimum, we can contract by the atom in the chain, and that fixes everything else. Okay, so next I want to move on and talk about the zip construction for minor posets. And for it to set up a little bit of background. So let's do that. Graded poset, which has a minimum and a maximum, is said to be Eulerian when we satisfy this alternating sum condition here. In other words, this is saying every interval has an equal number of odd and even rank elements. This is equivalent to the condition that the Mobius function takes values of plus or minus 1 depending on the length of the interval. A motivating example of Eulerian posets are face lattices of polytopes. This alternating sum condition is just saying that every interval of the poset satisfies the Euler-Poincare relation. More generally, face posets of regular CW spheres are Eulerian. And on a more algebraic side, intervals and Bruhat orders of Coxeter systems, as well as lattices of regions of oriented matroids are Eulerian posets. All right. And so we're going to show with this construction later that these minor posets have to be Eulerian. We also need some notions about the order complex of a poset. For a poset, the order complex is the simplicial complex which can consist of all the chains in the poset. We say poset is a PL sphere when there's a piecewise linear homeomorphism between the order complex and the boundary of its simplex. And if you like, this is equivalent to saying there are combinatorially isomorphic simplicial subdivisions of the order complex and the boundary of the simplex. We're really going to be interested in not looking at the order complex of the poset itself, but this proper part, which has the minimum and the maximum removed, because in the order complex, the minimum and maximum pyramid over the rest of the complex, and so that makes things a little uninteresting. Some examples of PL spheres include proper parts of face lattice of polytopes, as well as the proper part of any interval of Bruhat order for a Coxeter system. And it'll be important for later that the proper part of, or rather that if a poset has proper part of PL sphere, so does every interval. I also need to introduce this zip operation. This was introduced by Nathan Reading. Use it to study Coxeter system Bruhat orders. But in order to define a zip operation, we need a zipper in the poset. The zipper is an element Z, which covers exactly two elements. And these two elements have to have the same downset in the poset. And the last condition is that the zipper is the join of the two elements it covers. So here I have a depiction of zippers in the zip poset. The zip poset we get by identifying our zipper, the two elements it covers, and we sort of get the induced order relations, that anything below any of the three elements in the original poset is below the new element in the zip poset, and the same thing with being above. So on the top left is the Haas diagram of our original poset P, and this is what a zipper might look like. Below that is what the Haas diagram of the zip poset might look like. And then on the right, if your poset was the face poset of a regular cell complex, it might look like this. The zipper corresponds to a cell which has exactly two cells making up its boundary, and then the zip operation is contracting that cell and identifying the two cells on its boundary. So some results about the zip operation. It preserves the properties of graded and thin, well, as a package together, not separately. And if the proper part of the original poset is a PL sphere, so is the proper part of the zip poset. And then it also preserves the Eulerian property. So the zip operation is rather well behaved in these respects. And I'm also going to use this characterization of Bierner's of face posets of regular cell complex. Any poset which satisfies these three conditions is isomorphic to face poset of a regular cell complex. So we have to have at least three elements, a unique minimum and maximum. And then the interesting thing is that all the open lower intervals have to have an order complex homeomorphic to a sphere. Okay. Now here's the statement of my main theorem, the zip construction here. So if we're given two generator-enriched lattices, LG and KH, and we have a strong surjection from LG onto KH, then the minor poset of KH we can get from the minor poset of MLG via a sequence of these zip operations. So in short, strong surjections introduce or induce zip sequences between minor posets. And since this zip operation had all these nice properties from the last slide, we get a few nice corollaries from this construction. That for any generator-enriched lattice, which has more than one element, the minor poset has proper parted PL sphere, that it's Eulerian, and furthermore, from Bierner's characterization, it has to be isomorphic to the face poset of some regular CW sphere. So we have the geometric way to view these minor posets, which is kind of nice. All right, so now I want to give a sketch of the proof of this theorem here. On the right, I have a depiction of mapping from the Boolean algebra to the running example here. We're mapping 1 to A, 2 to B, 3 to C, and because it's join preserving, 1, 2 also goes to B, and then those three elements at the top all go to 1 hat. The first idea in this proof is to take our strong surjection and then to break it up into a sequence of maps which only identify two elements. We have to be kind of careful how we do this to make sure we keep a lattice in between. So to get that ordering right, we view the map as a congruence, just saying two elements are congruent when they have the same image. And we're going to view building the target generator-enriched lattice by identifying everything which is congruent, sort of two things at a time. And to get the order that those identifications right, we look in this poset on the diagram edges where we go up in the poset by sort of joining an edge with a third element. On the bottom, I've got a depiction of the edge poset for the Boolean algebra there. And then as we make these intermediate congruences by identifying two elements at a time, these will preserve joins and thus define a lattice precisely when the set of edges where we've identified the two elements form an upper order ideal in this poset. So we just have to go top down in that poset at the bottom, identifying edges. So here in this example, we have to identify 2, 3, and 1, 2, 3 before we can identify 3 and 1, 3. Okay, so this is a process by which we'll factor the strong surjection into these smaller maps where I identify just two elements. And with that, we can just consider the case where our map F identifies X and Y. Since it's join preserving, it's not hard to show that, in fact, we need that X is, or in fact, we have X is only covered by Y. In the next step, we induce a map between the minor posets. Big F is defined just by applying little f to the generating set in the minimal element of a minor. We want to show that the identifications made by this map F on the minor posets can be realized via zip operations. The next step is that we show the non-trivial fibers of this map F are these triplets here, where Mi is a minor which contains both X and Y either as generators or a minimal element. And then the other two minors we obtain by removing X and Y. So when we remove Y, that's necessarily by deleting it. Removing X, if it's the minimum element of M, we have to contract Y, and otherwise we delete X. And then to complete the proof, we just have to show that these elements mi are a zipper as we when we go up in this poset and we zip rank by rank. So we start by zipping everything, which is rank 2 and then rank 3 and go up. All right, so there's 3 conditions we need to check for that it's a zipper. And the first is that this covers only 2 elements, that it's the join of these 2 elements, and thirdly, that the 2 elements mi covers have the same downset. This third condition we actually get for free from thinness. We started with a graded and thin poset, so as we apply the zip operation, we still are graded and thin. And yeah, the third condition just follows from the thinness. Okay, but to show that mi only covers these 2 elements, more or less follows from construction. Everything that it doesn't cover besides these 2, we still have x and y either as a generator or as a minimum element. And part of that uses the fact that x is only covered by y. But what that means is that they're zipped at some point. They're zipped before mi, and then when we zip them, we reduce their rank. So that by the time we zip mi, it's no longer covered. And then the last thing to check is that mi is a join of these 2 minors, mxix and yiy. And to do this, I use a characterization of joins in minor posets to show it's a join in the minor poset of LG when we started. And as we go up rank by rank, zipping, it will keep that property, won't destroy it. So that finishes the proof of the zip construction. Here I have an illustration of the example playing out. So the top left, the Boolean algebra, and we're looking at that same map going to the lattice on the bottom right. Next to the Boolean algebra at the top left is a regular cell complex, which is combinatorially isomorphic to a cube, and its face poset is a minor poset for the Boolean algebra. So in the zip construction, we're going to identify along the 3 edges, which are highlighted in the Boolean algebra. We have to start with one of the 2 top ones. I started with 1, 3, and 1, 2, 3. When we identify those 2, we get the generator enriched lattice at the top middle. And then on the complex, we have to we start by zipping the corresponding edge, which is the one along the back. And so we get the complex in the top middle. And that's the only step in this case. So that's face poset of that is the minor poset of the lattice next to it. In the next step, we identify the 2 elements along that top bolded edge, and we get the lattice in the bottom left. On the complex, we contract the corresponding edge to get the complex in the top right. And then you'll see this triangle along the back and the top middle complex is turned into a 2-gon. This is corresponding to the minor, which is the upper interval above the 3rd atom in the lattice. And in that minor, we've identified 2 of its generators. That means we have to zip the corresponding, we have to zip that in the zip construction. So we zip the 2-gon, contracting it to get an edge in the complex on the bottom left. And then the last step, we have to identify the 2 edges, or the 2 elements in the lattice, which are connected by that last bolded edge. We zip that edge on the complex, and then we get another 2-gon in the middle, now corresponding to the minor, which is the upper interval from the 2nd atom, and that lattice on the bottom left. In that minor, we've identified the minimal element with a generator, so we need to zip it as well. And when we zip that 2-gon, we get the complex on the bottom right. And yeah, that complex has face poset, the minor poset of this generator enriched lattice next to it. So the last thing I want to talk about is some inequalities we get for the CD index of these minor posets from this zip construction. First, I'll find the CD index, review that. So we have a ranked poset with a minimum and a maximum. We start by defining the AB index. A and B are non-commutative variables. And we set up these chain weights here, where a chain gets B for every rank that it has an element in, and an A minus B whenever it skips that rank. The AB index of the poset is defined by summing over all the chains which contain 0 hat and 1 hat and taking their weights. To define the CD index, we set C equal to A plus B and D equal to AB plus BA. And if we can express the AB index as a polynomial in C and D, then that polynomial in C and D is the CD index of our poset. So you should think of the CD index as a very compact way to enumerate the chains in the poset.
So how restrictive is this if? So how often can we actually define the CD index?
I don't have a great sense of how often, how to say, but there's a set of linear equations you get on the flag vectors, or the the number of chains going through certain ranks in the poset, which you have to satisfy, called the generalized then Somerville equations. But a particular nice class is Eulerian posets. This is the theorem of Baer and Valera, so that every Eulerian poset has a CD index.
Okay, thanks.
Here I have a quick example written out. We look in the Boolean algebra of rank 3. There I've written out all the chains along with their weights on the right. So then below that, if we sum over all the chains, we get this polynomial and multiply out, and that can be expressed as C squared plus D. Okay. A few results for CD index that I need. First is this non-negativity result. The CD index of any Gorenstein star poset necessarily has non-negative coefficients. Here, Gorenstein star means that the order complex of the proper part of the poset is a real homology sphere. And that's sort of more general than we need. In particular, if we have a poset whose proper part is a PL sphere and is Eulerian, then we have non-negative coefficients in the CD index. So that means this theorem applies to minor posets as well as anything that we get by zipping minor posets. Nathan Reading, when he introduced the zip operation, gave this formula for how it affects the CD index. If you zip an element which is not the maximum, then we subtract off this this term here, the CD index of the lower interval up to one of the elements the zipper covers, times D, and then times the CD index from the zipper to the maximum element. So in particular, if you have if you started with a poset whose proper part is a PL sphere, then the same holds for its intervals, and this term here we're subtracting has non-negative coefficients, and so the zip poset has smaller coefficients. And then on the other hand, if we zip the top element, this is not hard to compute that it corresponds to losing a right factor of C from the CD index. Okay, so with these results and the zip construction, I get this corollary here. So same hypotheses as the zip construction theorem. We have strong surjection from LG onto KH. And then the CD index of the minor poset of KH, when you sort of lift it up by this power C on the right, is bounded above coefficient-wise by the CD index of the minor poset of LG. In particular, if we start with the Boolean algebra, this minor poset is isomorphic to cube. We find that the CD index of any minor poset is bounded above by the CD index of the cube of the same rank. Okay. And then at the bottom, I have an example here. Looking at the same 5-element lattice from before, you can compute that the CD index of the minor poset is C cubed plus 2CD plus 3DC, and the CD index of the minor poset of the Boolean algebra, or of the 3 cube, is C cubed plus 4CD plus 6DC. If you look at the difference here, which is the 2CD corresponds to the 2 two-gons that were zipped in the construction, and the 3DC corresponds to the 3 edges in that construction. Okay, so that's all I had for today, for the talk.
All right, thank you very much. Are there any questions? So I can start with one maybe. For this CD index, I mean, that's a polynomial. Can you somehow say what type of polynomials we can get for that index? Or can we get anything?
Yeah, there's a few things. One thing is that they have to be homogeneous when you consider C to be degree 1 and D to be degree 2. So you can see in those examples, they're all, each monomial is degree 3 like that. Another thing is that the coefficient on C cubed is always 1. And if you just look generally at anything with a CD index, I'm not sure that any like particular bounds besides that are known. There was one thing where if you plug in 2s for C's and D's, you should get the number of saturated maximal chains in the poset.
Are there any other questions? Oh, sorry.
Oh, nothing.
Are there any other questions? That doesn't seem to be the case. So thanks again to William. I will